can write. If C is an element of the real numbers, so that'd be just some scalar, okay? That's a constant. So this is called a scalar. Okay, so some specific number, and if we have A vector is the vector given by A1, A2 vector, then what we can do is take C times A vector and get CA1, CA2. Whoops, CA2. Okay, so basically it's pretty simple. We just multiply each position by that constant. This would also equal A vector times C, so it is okay to multiply on the right times C. And why is that okay? A vector times C, because that'd be, this equals A2 times C, and this equals A1 times C because of the commutative law of multiplication, right? So these are real numbers. A1 and A2 are real numbers as well. So we do have the commutative law, which switches order for multiplication. Remember, in real numbers, A times B equals B times A. So 5 times 4 equals 4 times 5. So that's pretty obvious, but that's, we switch the order, that's commute. We commute the order. So we do have some different value laws that I'll go over, but this is one of them, the commutative law of scalar multiplication in the vector space. So, but let's just look at this. If I have, I got to clear my screen. If this is a vector right here, and I want 3 times a vector, well, what would that look like? It'd be 3 times as long, right? So this is 3a vector. So that should make sense. And of course, as long as it's parallel, just we need the magnitude to be 3 times as big, right? So in the same direction. So let me just look at another one. If here's one, if I've got b vector here, well, we could have minus b vector would be the same length, ideally. Anyway, so this is minus b vector, same vector, opposite side. So multiplying by a negative scalar, things of that nature. I could do one more here. If I've got c vector right here, I could have 1/2 c vector, should be half that length. So how's that? So this would be like 1/2 c vector. Okay, where that's a capital bold C, or a capital C with an arrow over it. So that'd be 1/2 times c vector. All right, so pretty easy on that. And just note a couple of things. If we have the norm of c times a vector, looks like I'm using purple for the Wildcats, or whatever version of purple they have here. That's about as good of purple as they got. It's more plum, really. But anyway, this is just going to be the absolute value of c times the norm of a vector, the size of a vector. Okay, so remember, the norm is always going to be a positive. So if c happens to be a negative constant, we want to take the absolute value of that here. So anyway, so now let's get some constants. So we got results, laws. This is in the middle of page 6. So we've got a vector, b vector, and c vector are all vectors. Okay, so these are elements of V2 vector, 2-dimensional vector space, and c and d, little c, little d, are scalars. They're elements of the real numbers. Okay, then we have certain theorems. So first of all, first one, we've got a vector plus b vector is going to be the same as b vector plus a vector. Well, in the once again, we're switching the order here. So in real, we have, that's commutative property of addition. But what is this? This is actually the commutative property or commutative law of vector addition, which it looks like in my notes, addition was left off from vector on theorem number 1. So vector addition, and very similar to what we have with real numbers, right? So there are some things that are mirror images to the real number worlds, but there are some that are not the same. So another one that we have, I'm going to write this a different way for number 2, I'm going to have the parentheses. If I add A vector plus B vector and then add C vector, and of course that needs to be defined, then that's going to be the same as if I move the parentheses and add B vector plus C vector first, and then add A vector on the left. This is a theorem also, and so I'm changing grouping. So if you remember, I don't know if I said that, but that's the associative law. So cut the ass in half, Jenny Craigit, or what's a keto diet, whatever, cut the ass in half, and you got left parentheses, you got 2 of those, you got right parentheses, 2 of those. So here's my left parentheses, here's my right parentheses, right? But you're shifting the grouping. So we're changing the grouping. In this case, we're doing it over a vector addition. So this is the associative law of vector addition. So once again, number 2 in your notes doesn't have the plus sign or addition, the word addition at the end, which it needs at. And then of course the additive identity in real number world is 0, because you add 0 to any number and you get A plus 0 is A, right? So we also have that in the vector world. So we have A vector plus 0 vector. Now 0 vector has to be the same order, so that 0 vector has to be a 2-dimensional 2-space 0 vector. So this is actually, in this case, 0, 0. Okay, we can get into 3-space vectors, etc., but right now we're talking about 2-space. But anyway, this is going to equal A vector, and of course we also know that this equals 0 vector plus A vector because of number 1 up here, right? So we have some different properties. So this is the additive identity for vector addition. So the additive identity for vector addition. So we want to be specific on that. And then of course number 4, she looks like my person didn't really put them on all of them. We also have an additive inverse. So in the real number world, we had A plus the opposite of A gives you the identity. So basically, what do you add to a number to get the other number? This would be the additive inverse. So in this case, it's the additive inverse. We can also do this with vectors. Okay, and then of course, if I do it with multiplication, let's talk about that. What do you multiply A by to get the multiplicative identity? Multiplicative identity doesn't change it, so A times 1 is A. So the multiplicative identity is 1 in real numbers, and of course, we'd multiply by 1 over A is the multiplicative inverse in real number world. Okay, multiplicative inverse, I could also write that as A to the minus 1 power, couldn't I? So that equals 1 there as well. So let's look at what that is in vector world. Somehow, there's my screen, all right. Anyway, so then I've got, Isaac's gonna leave now. I had to get logged in. So I'm gonna keep going so that Isaac can watch this as well. I'll kind of finish the chapter. Isaac, have a good day. I'll see you later on. Jordan, have a good weekend. But anyway, I'll keep going here. And yeah. What is it? No, turn them in when Jordan does. So, all right. So you can just turn them in when we all meet again on Tuesday. So for 10-1. Anyway, so then I've also got, so A vector plus this is number 4 here, A vector plus the opposite of A vector is gonna, equals the 0 vector in 2-space. So these are all 2-space vector addition, right? So we have that as well. And then we can also say that number 5, so what is this? This one up here, this is the additive inverse for vector addition. Okay, so number 4 is for vector addition. So we need addition on there too. And then we can also multiply by scalars. So if I have couple of things, I don't think I wrote it in here, but I already wrote one earlier, that we have C times A vector equals A vector times C. Okay, so this is the commutative property of scalar multiplication. So this is commutative property of scalar multiplication in the vector world. Okay, so we have that one. This is another, you could put that as number 9, I guess, which is Ix. All right, but anyway, number 5, we've got a scalar C times scalar D, a vector, and once again, we can switch the grouping. Anyway, so I can multiply C times D first and then times a vector, and if you can prove this out by, actually showing it. But this is the associative law. We're changing the grouping. So usually I start with the right side and go to the left side. But anyway, in shifting the grouping there is okay, as long as both of these are scalars. C and D both have to be scalars. So you got to be careful. We do not have this if I have a vector times b vector. So notice that we don't have some of the properties of vector multiplication that we do in the real number world. And there's a reason for that, and we're going to have different definitions of that coming up. So we do have that C, scalar C times a vector plus b vector. I can go ahead and distribute that out over here. And so it's C times a vector plus C times b vector. Just by definition of that, once again, we can prove this because this would be C times the vector. What if this is A1, A2, and B is B1, B2? This is A1 plus B1, and then A2 plus B2, right? And if I take C times that vector, I'm just going to multiply each part times C, which is, CA1 plus CA2 because of the distributive law, CB1 for the first one, and then CA2 plus CB2 because of the distributive law of real numbers, real number multiplication over real number addition, but that ends up equaling this, CA plus CB. So, because CA is CA1, CA2 vector, and this one is CB1, CB2 vector, and if you add those together, right, CA1 plus CB1 is right there. So anyway, that's a proof, kind of sloppy. I apologize for that, but anyway, so we'll clear that off. But anyway, so we do have that as the distributive law of scalar multiplication over vector addition. So you have to be very careful how you say that one. Scalar multiplication, distributive law of scalar multiplication over vector addition. And then of course, we have another version of that, which I think is number 7, and that's C plus D times a vector equals CA vector plus DA vector. And this is the distributive law of scalar multiplication over scalar addition. Okay, once again, you could step this out, show what this side equals and show what that side equals, and verify that those are equal for proof on that. But anyway, so that's a little different version. So in this case, what did we have in real numbers? We had A times the quantity B plus C for real numbers is AB plus AC, right? That was the distributive law of multiplication over addition. We would just call it the distributive law, but this is real number multiplication over real number addition. And so we have two, and so we only really had one type of distributive law in real numbers. We actually have two types of distributive laws when you have scalars and vector addition and that stuff. So anyway, so a couple of differences that we have here in the vector space V2. Okay. By the way, a lot of this stuff, if you're in 3 space or things of that nature, would also apply, or in space vectors, which we can't visualize necessarily what those vectors look like, but we could define, a vector that has 4 components. And then last but not least, we have, if I can get it, the multiplicative scalar identity for multiplication is 1, because 1 times a vector is a vector, right? So this is the scalar identity for multiplication. Notice that this also equals a vector times 1. And this is an easy proof as well, but that was the last one that was on your list. And of course, I put number 9 in there as well to be, and I'm going to put it in my notes, that C times A vector equals A vector times C, which is the commutative property of, or commutative law of scalar multiplication. All right, so anyway, so I put that in my notes too. So let's move on. So we do have a lot, but we got to be careful. So I do want to say what we don't have. What don't we have? If I have A vector times B vector, you know, it'd be nice to say, hey, does that equal B vector times A vector? Well, right now, we don't know what this means. How is this defined? So we've defined addition and subtraction in vector space, but we have not defined multiplication. So that's going to be future sections in chapter 10. So we actually are going to have two ways. One's going to be a dot product, and one's going to be a cross product. Okay, product means multiply, right? So we're going to have two different ways that we're going to define on how to multiply. So right now, we don't have this property, which, you know, in the real number space, A times B equals B times A, we're just switching order, is the commutative property of real number multiplication. We do not have that at this point. So we got to be careful. The only ones that we have are dealing with scalar multiplication. So actually, we do have a third type of multiplication, and that's scalar multiplication. But notice what I wrote up here was two vectors, A vector and B vector, trying to multiply those together. So there are two different ways that we'll cover, not in this section. Okay, so just giving you a heads up where we're going. And then I started doing this yesterday, but just real quick, if we have vector space, and if I go, I'm going to go to the right, I'll use red. So if I go over 1 up 0, this is going to be I vector or I hat. I'm going to use a hat there. If I go up, I'll use blue for that. If I go up 1 unit, so this is position representation of vector 0, 1. Okay, this is going to end up, we're going to call that J vector there. So what I'm going to do now then is go back. I want to stick with the purple theme for the Wildcats. All right. So anyway, if I have a vector in V2, and in this case, I'm going to be over, let's see, let me go over 3 and up. I'm going to make it a little bit different in the book. I'm going to go up 5. Okay. Then what I'm going to do here, so this is vector over 3 up 5, but I could rewrite this as 3 times I hat plus 4 times J hat, or 3I vector plus 4, it's not 4, sorry, this is a 5, isn't it? So plus 5 J vector, okay, different than the one I wrote in the notes. So anyway, so we have that. So in general, if I have a vector A1, A2, then I'm going to be able to rewrite this as A1 I hat plus A2 J hat. So this is the two-space vector representation. What's the difference between these two? This has two different components, right? Is basically with order there, similar to an ordered pair. But this is a linear. This is a so the top one here is two-dimensional. This one has a two-dimensional graph, but it's one thing. It's one output there. Okay, so there's some advantages to writing it in different ways like this. And what we'll notice is that in 3 space, we could do a similar thing. So I don't know if I can draw 3 space or not. I'm going to try. But 3 space kind of looks like this. We got the x-axis coming out, the y-axis to the right, and the z-axis going up. And we have a 90-degree between each one of those. But if I've got something out here in the first octant, we kind of talked about that, where, hey, this is A1, A2, A3 for A vector. So now this is 3 space. So this is an element of 3-dimensional vector space. I could write this as, what I can do now is I can let I hat in this case would be coming out the x-axis 1 spot. So that'd be 1, 0, 0. J hat would be 0, 1, 0. And K hat would be 0, 0, 1. Okay, so what I could do is I could rewrite this vector as A1 I hat plus A2 J hat plus A3 K hat. So that'd be a different representation of a 3-space vector. And once again, both of those are element of V3. I'm going to use a different color here if I can. Maybe. And so I'll just kind of go this way. Red was to the right, but it was actually the X. So there's I hat right there coming out the X-axis, 1 spot, right, 1 unit. And then I think we used maybe blue for the Y. That's coming out 1 unit there, which this is the blue vector J hat there. And then I can use a different color. I'll just use green since that's different. I can go up, and so that's K vector. Once again, I vector, I hat was out 1 to the right 0, up 0. So I know normally the Y is up, but when we have 3 space, we actually let the Z vector or the Z axis go up. Okay, X comes out, Y to the right, Z up. So we'll get there as well as we go. So, okay. Anyway, so we can have 2 dimensions, 3 dimensions. We could actually have n dimensions, right? So we can have a lot more dimensions than that as well. And then, so let me keep going here as long as I can. And anyway, so remember that we have from before, we had if a vector was A1, A2, then we knew that A1 equals the norm of A vector times cosine theta, and A2 equals the norm of A vector times sine theta, right? Where theta is the angle away. So here's A vector right here, and this is my theta. Okay, so we had this from before as well, right? So what we could do is we could say A vector is A1. So if I have A1 I hat plus A2 J hat by our new way of writing that, then we can just plug in A1 right here. So that's norm of A vector cosine theta plus norm of A vector sine theta, which of course we could pull out the norm of A vector out front by the distributive law. Remember, that's just a number. Norm of A vector is a scalar or a number, and then times cosine theta plus sine theta. Okay, so we have another way that we can represent a vector there. Excuse me, I forgot my I. Sorry. Let me show you with a different color what I forgot. I forgot my I hat and J hat, so I needed my I hat here and my J hat here, and so I also need it here. So I got my I hat, my J hat. Okay, so I can rewrite A vector as the norm of A vector times the quantity cosine theta I hat plus sine theta J hat. Okay, all right, so we're getting a lot of good stuff going here. Let me get back to my color. So far this is actually working out pretty good for me on this. So we have an example in the book, or on, I'm in my notes, I'm on page 6.5 basically. So I'm gonna use a different example. So let's just look at an example. Let's draw one up. Let's have, let's go A vector right here, and let's say I'm over 4 up, well, 3. Let's just do this one. Okay, there's my theta. And so what can I do? I can say that what is A vector? A vector is A1, A2 is going to be over 4 up 3, right? So that's the position representation. So then I'm going to be able to take the norm of A vector is the square root of 4 squared plus 3 squared, which is square root of 16 plus 9 square root of 25, which is 5, right? And it's the norm of A vector is always positive. So the norm of A vector is 5. So that one's pretty easy. So what we can do is know that, hey, so A1, what did we say on the previous slide? We said A1 is the norm of A vector times cosine theta, right? And so if I do that, plug that in, what is A1? Well, we know what A1 is. It's 4. So 4 equals the norm of A vector, which is 5, times cosine theta. So what I can actually do here then is figure out what theta is, because the cosine of theta is going to be 4/5, right? So just solving that, which implies theta is the inverse cosine of 4/5. And so we can do that and then make sure you're in radian mode or whatever, and go from there. So I did not bring my calculator in, so I'll let you do that to come up with the actual angle there. And of course, we could have also done the other one with A2. So if I have A2 is norm of A sine theta, then of course A2 is 3, right? So 3 equals 5 cosine theta, not cosine, sine. Okay, so then sine of theta would actually equal 3/5. So theta would be the inverse sine of 3/5. Okay, and then, you know, radian or degree mode, pay attention to that. But anyway, so either one of them is going to give us that angle theta. We don't have to do both, but they would actually agree, and we just need to know which quadrant you're in. Okay, so sine is your height. Anyway, so sine is positive in quadrant 1, and cosine is positive because that's your x. So cosine is positive, sine is positive. So just pay attention to the quadrant when you're doing those. Okay. All right. And let's see, what else do we need here? There is a different way that we could write that if I pulled the norm out. So, well, I'll skip that. Just kind of look in the notes because I use different numbers, so I'm going to confuse myself since I can't look back at that screen. So anyway, well, no, I think I can. So on my example, I had cosine theta was 4/5, right? And I had sine theta was 3/5. So I'm pretty sure that's what I had on that previous screen there. So if I do that, then I can write a vector, remember, as the norm of a vector times cosine theta I hat plus sine theta j hat, right? So that was another definition. Of course, we have the norm of a vector was 5, and so times 4/5 I hat plus 3/5 j hat. So I was able to remember what we had, luckily, on my example, which was a little bit different. So that is another way to write a vector. So if you note, one thing that we can do is pull out the norm and then divide by that norm. So what do I mean by that? The norm of a vector was 5, right? Okay, so we knew that. So what I'm saying here is the if a vector in my example was over 4 up 3, right? So anyway, it was so we could write that as 4i hat plus 3j hat, right, with the alternate definition. And then if I want to rewrite it in a different way, I can pull out the norm of a hat from this. And since I pull that out by multiplication, so let me just start that process. If I pull a 5 out, well, I didn't have a 5 in here. So to undo that multiplication that I don't have up here, I have to divide by the norm of a hat as well on each part. Okay, so basically I got to take 4i hat plus 3j hat all divided by 5, right? So to undo the multiplication by 5, I divide by 5. Of course, then I could rewrite this as 5 and then divide each part by 5. So 4/5 I hat plus 3/5 j hat. So I can do that as well. Okay. So that leads us to a theorem, and then we're going to almost be done with the section formally. So here's a theorem, proven fact. We're going to let a vector equal a1, a2, which of course in two-dimensional vector space, this is a1 I hat plus a2 j hat. Okay, so we know those. So we have that. Then we're going to look at the unit vector in the same direction as a vector. Okay, the unit vector, what's that mean? Magnitude equals 1. So a unit vector has a size of 1. So a vector had a size of 5 in my example, right? But a unit vector is going to be in the same direction and have a magnitude of 1. So the unit vector in the same direction as a vector is going to be given by u vector. So we're going to call u vector the unit vector in the same direction as a vector. And what this ends up being is it's going to be a vector divided by the norm of a vector. Okay, so we're going to have a vector and then divided by its size. So when you divide it by its size, it's going to end up equaling 1. But anyway, so this ends up being a1 I vector plus a2 j vector divided by norm of a vector. So, and I could divide each part, right? So that's just real number rules here. So it's a1 over the norm of a I hat plus A2 over the norm of A vector J hat. Okay, so we got that. But I like to think of it as the unit vector in the same direction is A vector divided by the norm of A. Okay, so, and of course, what's the norm of the U vector? The norm of the unit vector, so the magnitude that I was talking about, so the norm of U vector always equals 1. Okay, always equals 1. So let's go back and look at my example, once again, if I can remember it. Whoops. Clear that. Go back. All right, and so we had my A vector was 4, 3, which was 4i plus 3j. And of course, we had a picture of this, right? So over 4 up 3, I believe is what I had. So there was my A vector. And the question is, what's U vector? Well, U vector, and I'm going to use a different color here. I'll use red. That seems to contrast. So the unit vector U is going to be in the same direction. It's a vector in the same direction as A vector, but it has a size of 1. Okay, so that's going to be the unit vector. So once again, the same theta that we came up with by taking the inverse cosine of 4/5 is the same theta as for the unit vector as well. But anyway, so what I can say then is U vector, whoops, let me go back and change my color. So U vector is going to be A vector divided by the norm of A vector, which is 4i hat plus 3j hat, all divided by 5, because that's the norm of A vector, right, which we came up with before. So if you prefer, I can write U vector as 4/5 I hat plus 3/5 j hat, and after I made sure I had my I hat right here and j hat in there, this is exactly what we had previously, right? So anyway, that's the unit vector in the same direction as A. Once again, this is the formula that I like to remember. It's just A vector divided by its size, because we're going to divide that down to make it have a size of 1. Okay, and now let's just do one more example. So I'll go over that last example. I think I still have time for it. Hopefully I don't get cut off. Whoops. Clear this out. Go back to my drawing and my color scheme. Wildcats in the house. All right. So just looking at an example that I have on the top of page 7. So we've got A vector is -3, 4, and B vector is 5 - 2, and we want to find U vector, so a directional unit vector in the same direction as B vector minus A vector. Okay, so as B vector minus A vector. Well, in this case, what is B vector minus A vector? This is in your notes. But anyway, B vector is 5 - 2, and I'm subtracting away -3 -4, or +4, sorry, +4. And so this is gonna equal, so 5 minus a -3 is 8, and -2 -4 is -6. Okay, so this is, if I rewrite this B vector minus A vector, then it's gonna be 8i minus 6j, right? If I write it in ij notation. And then of course, what can I do to find the unit vector in the same direction? So I'm going to go ahead and erase, give myself some room here. But if I want the unit vector in the same direction as that, then the unit vector is going to be B vector minus A vector divided by its size, right? By the norm of B vector minus A vector. Well, I have to figure out what this norm is. And of course, that vector, B vector minus A vector is, what did we say? It was 8 minus 6, right? 8 minus 6. So that norm is going to be the square root of 8 squared plus minus 6 quantity squared. So 64, square root of 64 plus 36 is square root of 100 is 10, right? So anyway, so this is going to equal, be equivalent to, so what do we say? This was 8i minus 6j. So it's 8i minus 6j I hat minus 6j hat all over 10, right? So that's the unit vector in the same direction. Of course, that is not simplified. I could rewrite that as, 8 over 10 I hat is 4/5 I hat. Whoops, not plus. I need a minus. Starting to figure out the software here. 6/10 is 3/5, right? J hat. So I have that. Now, if you would rather write that in vector notation like this, what would the unit vector be? We could say, hey, this is 4/5 and then minus 3/5 with a vector notation is another way to do that. So both of these are equivalent answers for the unit vector in the same direction. So hopefully that's all good, and enjoy your weekend. There's no school tomorrow for you guys. There is school for DMAC, so I may end up starting into section 10-2. Haven't decided that yet. I'll let you know. Reach out with any questions, but I'm completely done with 10-1 and expect the next time we meet in class that you are as well. So anyway, we'll talk to you later. Go